Hi everyone, how are you? Students, in today's lecture we will discuss about energy loss from stars, the different regions of the sun and also the process of conduction, convection and radiation from the sun. Students, at the core of all stars there's a glowing nuclear furnace. We can be sure of this because we can measure how many neutrinos are streaming out of the sun with experiments like the Sudbury Neutrino Observatory. This observatory is shown in this figure. This property of neutrinos that they can pass through the core of the star virtually unimpeded is because neutrinos are weakly interacting particles, which is to say that they do not interact with electromagnetic forces. Light particles or photons do interact electromagnetically and thus they have difficult time leaving the core of a star. The innermost region of the sun, extending from the center to about one quarter of the radius of the sun, is the region where fusion takes place. This is aptly named as the thermonuclear energy core. In this innermost region, the temperature, pressure, and density are extremely high, suitable for elements to combine in the process of fusion. And here the temperature is about 1.55 multiplied by 10 raised to power 7 Kelvin. Or you can say roughly 15 million degrees. The density of the material is nearly 14 times the density of lead and the pressure is almost a billion times the atmospheric pressure here on Earth. In order for energy to escape from this region, it needs to be carried away by one of three processes like conduction, convection or radiation. Students, conduction, which is the propagation of heat through a solid, is inefficient in the sun because, well, the sun isn't a solid. In this centermost region, extending to about three quarters of the diameter of the sun, energy is carried away by radiative processes, the motion of photons. Students' photons take about 2.3 seconds to cross the sun's nearly 700,000 kilometers radius. Photons are impeded by the material of the sun. Instead of 2.3 seconds, photons take an average of 1,70,000 years to escape into the space. This diagram represents the emission of photons from the sun. That's right, the energy we observe in the form of sunlight has been working its way to the surface of the sun for hundreds of thousands of years. Within the three quarters of the diameter of the sun, photons bounce around on very short paths, randomly walking their way towards the surface. Photons migrate towards the surface due to the temperature gradient. Each step taken by a photon amounts to about 1 centimeter and it would take you around 2000 years to walk 700,000 kilometers. But that's assuming that you would walk in a straight line. That's why we are taking temperature gradient. Eventually, the energy from the core of the sun stumbles its way to the surface. As you move outward, the average temperature of the sun drops. And at the boundary of the convective zone, it's cool enough for electrons and protons to join into hydrogen atoms, which happen to be very good at absorbing photons. Radiative energy transfer is no longer the dominant process and convection takes over. Atoms heated at the bottom of the convective zone becomes buoyant and mass of the hot atoms and plasma rise to the surface like bubbles in the lava lamp. Like you can say like the Beyonce effects. This figure shows the bubbles in the lava lamp. Students, then cooler gas at the surface of the sun sinks down to replace the hot gas that's rising and the process repeats. Once the hot gas reaches the sun's surface, energy stored in the heat of the gas is emitted as black body photons which can then travel across the vast distances of the space virtually unimpeded. Now that these are finally some photons escaping the sun. Students, this is all about this lecture where we have discussed about the energy loss from stars, and we have also discussed the process of convection and radiation that is taking place in the sun. Thank you so much.